Good day everyone. Welcome to the 13th International Conference on System Engineering and Technology. Myself, MD Saidur Rahman, MSc student of Jahangir University, Department of Statistics and Data Science. Today my presenting topic is transforming Tannery wastage into biogas and exploration of biogas production via anaerobic digestion. Contents of the presentation. Contents are introduction, methodology, experimental procedure, result analysis, findings, future direction, and finally conclusion. Introduction. Bangladesh is in the midst of severe and worsening energy crisis with a population of about 160 million. Living area is 1,47,570 million square. About 82% of total electricity comes from natural gas. As the demand is increasing and the reverse of the natural gas is decreasing, it is absolutely obvious to state that Bangladesh is a shortage of natural gas. The continuous depletion of fossil fuel is striking the concern into the search for the few energy source is mandatory. So we should focus our view on the alternative renewable resources like solar, biogas, biodiesel, wind power, tidal energy, etc. Biogas is one of the promising renewable energy resources in Bangladesh as an agricultural country. Biogas typically refers to a gas produced by the biological breakdown of organic materials in the absence of oxygen. Here is the topic is materials and methods. We are seeing here the schematic diagram of anaerobic digestion, first block, annual manure. Annual manure contains carbohydrates, protein, lipids, etc. After hydrolysis, we find the soluble organic molecules. Then acetogenesis process, we find the volatile fatty acid. Volatile fatty acid contains propionate and alcohols. After acetogenesis process, we find the hydrogen and carbon dioxide and also acetic acid. To combining the hydrogen and carbon dioxide and acetic acid, we find the biogas like methane after methanogenesis process. Here is the anaerobic digestion. The anaerobic digestion is the conversion of organic materials directly to gas termed biogas, a mixture of mainly methane, carbon dioxide, ammonia, water, hydrogen and nitrogen, etc. Anaerobic digestion is the process of decomposition of organic matter by microbial concentration in the oxygen-free environment. Here is the sample collection. Different types of tannery wastes are collected from the tannery at different places like Hemayatur at Sabah. Poultry droppings and cow dungs are collected from different places in Mirpur area. Before analysis and experiments, substrates are collected and different times and stored at 40 degrees Celsius temperature. Preparation of substrates. The limed flesh used as substrates are grounded to less 6 mm diameter using as a meat grinding machines. Cow dung was also used in the different proportion as substrate to maintain the carbon-nitrogen ratio. Here is the characteristics of substrates. Table 1 shows the parameter, lime fleshing, poultry droppings, and cow dung. Parameters are pH, total solid, percentage of volatile solid, moisture content, protein, chemical oxygen demand, nitrogen oxygen ratio, calorific value of lime fleshing, poultry droppings, and cow dungs. Here is the quantity of substrates, quantity of lime fleshing, poultry droppings, cow dung, and initial volatile solid concentration in the reactors. We are using here 5 reactors. The name of the reactor is RA, RB, RC, RD, and RE. Here is the concentration fleshing in milligram, poultry droppings, cow dung, inoculum, drain water, initial volatile solid concentration. We count or calculate the volatile solid concentration using this formula: weight of original sample minus weight of genuine dried sample divided by weight of original sample into 100%. Experimental setup. Here is the shown in the experimental setup of reactors in the laboratory. We are used to the lab of Institution of Engineering Technology, University of Dhaka for this research. We are here using every reactor is 4 liter capacity, but the initial volume of 3 liter in all reactors are through RD shown in table 2. The total gas production was measured at 24 hours intervals. Using the displacement method, the contents of the glass bottles were manually mixed after every gas measurement. Daily gas produced was recorded. The entire test was conducted at the temperature 40 degrees for 8 weeks. With temperature and pH probes initially for daily monitoring, the first outlet was utilized for substrate sampling while the second was utilized for the gas container. Here is the analysis: carbon and nitrogen contents of flashing domestic sewage and determined by the carbon, hydrogen and nitrogen element analyzer (TCD) detector. The potential contents are estimated from the nitrogen content by multiplying with 6.25. Total solid, TS and volatile solid and VFA were estimated according to the procedure recommended in the standard methods of examination water and wastewater. The volume water deflected from the bottle was equivalent to the volume of gas generated. The temperature and pressure that prevailed during the study period. Gas chromatography with TCD detector was used to measure methane content, carbon dioxide at 800 degrees Celsius to 1800 degrees respectively. Result and discussion. Characteristics of raw materials. The flashing has a significant amount of volatile solid at 81.32%, here dry basis is 9.5%, making it is a sustainable component. The protein content in the flashing was approximately 42.53%. The carbon-nitrogen ratio flashing was 2.51, which is the relatively low for optimal biogas generation. To increase the carbon-nitrogen ratio, the flashing was mixed with cow dung and poultry droppings. The pH of the flashing was quite high at 8.4, which is not favorable for biogas generation. The cow dung had a high buffering capacity, and the addition of poultry droppings provided various microorganisms essential for anaerobic digestion. Now we can discuss about the biogas generation. Daily gas generation. The volume accumulated with the varying levels of flashing is demonstrated in the figure 3.7. The generation of biogas from the mixer was delayed for a few days, but it is gradually increased the 15th day, with daily gas output showing a steady rise. However, after 45 days, the bacterial concentration in the substrate decreased significantly, causing a sharp decline in biogas production. Here is shown in the daily gas production. We draw the graph daily gas production by time. Figure 3 shows the daily gas production in the reactor array. The average daily gas production from the reactor array is 600 to 1100 milliliter, and the highest gas production is 23,500 milliliter occurred on the 31st days, and after 53 days the gas production almost ceased. Figure 4 shows the daily gas production from reactor RB. From reactor RB, the average gas production is 2,400 milliliter. After 29th day, the highest gas production is that, and the range of the gas production also within 550 and 125 milliliter. Figure 5 shows the daily gas production from reactor RC. The from reactor RC, the average daily gas production is 400 to 100, 1150 milliliter. And the highest gas production from the reactor RC is 188,000 milliliters observed from 24th days. In figure 6, the daily gas production of reactor RD is shown. The gas generation starting into days after charging the reactor with slurry. The peak gas volume is 1770 milliliter was observed on the 22nd day of the gas digestion period. The gas production almost ceased after 16 days of the digestion period. Here is shown in the daily gas production in reactor RA. The highest daily gas production after 25th day is on 1887 milliliter. Here is the shown in the cumulative gas production. Cumulative gas production in different reactor. Figure 8 illustrates the cumulative gas production in 5 test reactors RA to RE under varying organic loading of Tannery waste, solid waste, poultry droppings, and cow dung. After a duration of 8 weeks or 16 days, the reactor yielded the following cumulative gas production. Reactor RA with a volatile solid concentration of 62.86 gram per liter produced gas is here. Reactor RB with a volatile solid concentration of 60.41 gram per liter produced 56,716 milliliter of gas. Reactor RC with a volatile solid concentration of 65.56 gram per liter produced 51,226 milliliter of gas. Reactor RD with a volatile solid concentration of 63.78 gram per liter produced 50,626 milliliter of gas. Then reactor RE with a volatile concentration of 66.45 gram per liter produced 51,426 milliliter of gas. Furthermore, the specific gas production per unit volatile solid fed to the reactor as follows: reactor RA 0.8657 liter per gram, from reactor RB 0.9388 liter per gram, from reactor RC 0.7813 liter per gram, reactor RD 0.7938 liter per gram, and reactor RE 0.7739 liter per gram. Here is the findings: the reduction of chemical oxygen demand value from different reactors. We find the chemical oxygen demand from this equation. Chemical oxygen demand COD, chemical concentration of oxidation component in the sample divided by formula weight of the oxidation compound in the sample into ratio of the moles of oxygen into 32%. The process of the anaerobic digestion lead to a noteworthy decrease in chemical oxygen demand of the slurry. The mitigate in the chemical oxygen demand in figures 9 is so displayed. For reactor RA, RB, RC, and RD, the chemical oxygen demand rates are 49.22, 51.77, 47.70, 46.88, and 48.12%. respectively. The highest degree of chemical oxygen demand reduction attaining the highest gas production we are find from the RB reactor. Future direction we are develop and futurely upgrade the research. Here is it is individually reactor should be constructed for particular substrates like fleshing, cow dung, etc. Reactors should be observed for a least on 120 days. Temperature should be kept fixed. Should approach of commercial production. There is the final is conclusion. Currently, Tannery waste disposal practices in Dhaka city raise significantly environmental concern. The solid waste fraction on 88.32% volatile solid, fleshing waste along with not effectively degraded due to its low carbon to nitrogen ratio. Combining RB demonstrated the highest level of specific biogas generation, chemical oxygen demand reduction, and volatile solid reduction. Mixing fleshing waste with the other substrates improves the environmental condition for the desired anaerobic digestion in the biogas reactor. The methane content of the biogas produced for the substrates is also satisfactory. Biogas production from the substrates is hygienic and eco-friendly contribution to the pollution and reduce the pollution from the environment. Here is the key reference from our research. We are using mainly key references of 11 key references, and thank you.